This is our virtual Nature Journal Club gathering. Today, we're going to be getting ourselves ready for the upcoming equinox. So coming up on the 20th, we will have our autumnal equinox. I'm really excited for this event. Now, what we're going to be doing is just spending a little bit more time really giving this event some love and thinking about what is going on there, so that when Amelia, would you please bring me the globe? Thank you, Levy. We're gonna get a globe. What we're going to be doing is just trying to understand what's going to be going on this event, and then how to play with it, how to explore it in our journal. Oh, thank you. And it's neat because this is an event that, for our early agriculturalist ancestors, would have been, this is a big deal. This is so big that you make things like Stonehenge and other henges to track these significant events. It's a major turning point in the year. You know, at the end of our calendar year, you know, there's right when our calendar year ends, it's when we start a new calendar. But is there anything really significant going on there with kind of when we look at from the Earth's perspective? You know, maybe not. Maybe that has to do a little bit more with our calendars. But when we're talking about solstices and equinoxes, these are really, really big deals. And if you're kind of tuned into the cycles of the seasons, then when these things happen, you know, you have to time your planting right. If you do your planting at the wrong time, it's not going to end up very well for you. Either you're going to be killed by late frosts, and that wipes out what you did, or your plants are not going to be able to fully develop by the time it comes to harvest time. That's not going to work out well for you. So tracking these things was essential for survival. If you're a naturalist, it's also important for us to track these, because the whole rest of the planet, all the other living things, they're tracking these things, and that's what the cycles of their lives throughout the year are dependent on these phenomenon which we're looking at today. So whether you're looking at plants and when they bloom and when they bud, when they go to seed, whether you're looking at birds when they migrate, when they nest, they do all their things, whatever it is, being kind of tracking where you are relative to an equinox or a solstice is significant. So let's just take a moment here and play a little bit with what's going on here. If you ever look at here we go. If you look at a globe, they're always at this tilt, right? So the little bar that holds the globe on here, it's not oriented with the North Pole pointing towards the roof. The North Pole is tilted off at an angle. And the reason for this is that as the Earth goes around the sun, it's not oriented perpendicularly to the sun. It's at an angle. And so the globes are oriented at the same angle that the Earth is tilted away from its axis around the plane. If you imagine the plane of the orbit of the Earth, right? We're at a tilt from that, and that's why when you look at your globes, this bar that goes through the middle of it is at an angle. But wait, there's more, because it's much cooler than this. Because that little tilt in the axis of the Earth is responsible for all of this beautiful variation that we have in our year. If it was just straight up and down, there would be no winter, summer, spring, fall. It would just be the same. And you could get different sorts of conditions by going north and south on the globe, but you would be completely without these seasons. And here's why. Check this out. So if I, here we go. So if I hold this like this, if my head is the sun and I am shining on the earth, right? Because of the tilt of this, I am shining more here than up here. So if you were standing right here on the earth, you'd get more of my sun. And up here, I'd just be kind of glancing by you. Okay, that means summer, winter. But let's just take this Earth and bring it over here now, right? And when it's on the other side of the sun, I'm going to get this oriented again, right? So I have, so let's see. So here, no, here's my problem. So what I'm going to do is I am going to keep this bar that I'm holding. See where I'm holding this bar? I'm going to keep it on that side, always facing that wall. So notice here, I'm more sunny here than I'm up here, right? But look at this. Look at this now. It's now, the tilt is going the other way. All I did is I spun this around, kind of keeping that same angle, right? So this bar is still facing the same wall. I am now shining more directly on the northern hemisphere, right, than I am on the southern hemisphere. That means it's summer up here and winter down here. So because of this angle, at one point during the year, the southern hemisphere is getting more direct light, and at another point of the year, the northern hemisphere is getting more direct light. And exactly between those 2 points is a day where they both get the same amount of light. And it's more interesting than that, because when the northern hemisphere is getting more direct light, that also means that the day length is longer in the northern hemisphere and shorter in the southern hemisphere. So when it's summertime, the days are longer, because as you sort of spin around here, you're just sort of spending more time in this direct sunbeam zone. And that also means on the day that is just between those two, the length of the day and the length of the night, are they going to be different, or are they going to be the same? So you went from on one pole, on one side, you had long days, short nights, and the other one, long nights, short days. So somewhere in between those two, they have to equalize. And that is the equinox, equal night, equinox, equal night, right? So that's the root of equinox. And so this is the turning point, and we're about to come up to this is the tipping point. So if I'm living in the northern hemisphere, once I hit the equinox, from that point on, the nights are going to start to get longer than the days. Right now, my day is just a little bit longer than my night. But on the equinox, it's going to be just the same. Then it's going to start going the opposite direction. So what we're going to be doing is we're going to be celebrating this event by really tracking the position of the sun and looking around for signs of the season. We're going to look for direct evidence of what is happening ecologically around you in your area at this critical moment of the year. So the first thing that you can do is just to go out and have fun nature journaling. All right, so when you're doing that, you're documenting and describing anything that's going on. Anything that you notice on the equinox, get it down in your journal. Any little nature notes. What's going on? So that can be, if you're seeing bird activity, what are the birds doing? Really look at, like, what are you up to? What, and just, and kind of couch everything on this day in terms of, on this special day, what are you doing? We're here on the equinox. So birds, are you building your nests? I certainly hope not, right? But what are you doing? If you see migratory birds, are migratory birds starting to show up? Or do you think they're heading north or south? What do you think is up with that? And then we are going to, you're going to do the same thing with plants, right? So you see plants. Are plants starting to go dormant, right? Are plants, just starting to kind of come into their own? For this, it's going to be most interesting to look at wild plants. So ones in your garden, a little bit less interesting because you water them. You create these different environmental conditions for them. But if you're tracking kind of native wild plants, how that they have to respond to the cycles of the season a little bit more directly than things that we're kind of watering and adding fertilizer to and kind of putting little barriers over if it's going to be a frosty night, right? We kind of baby a number of our plants along, but not the case if you're one of those little critters out there in the wild. So what are they up to? So we want to document all these sorts of things in our journal. But we're also going to be checking out the path of the sun in the sky. And this is going to be cool. We want to pay attention to, I remember when I was little, I learned that the sun rises in the east and the sets in the west, right? And I remember being a Boy Scout and going out one morning and seeing where the sun came up. And I said, that's east. And later on, I told my scoutmaster, that's east. And he said, really? Get out your compass and check. So we got out my compass and I checked and it wasn't east. And I was freaked out. And, but there actually is a day where that happens. And you may get to discover this for yourself. So this is going to be cool because this is the significant date. So if you are mapping where the sun comes up, how high it goes in the sky, how long it's in the sky, when it sets, how you're going to get the day length. You're going to be able to compare the length of the night. You're going to be able to compare the length of the day. You're going to see how high the sun is going in the sky, where it started, where it ended, for your specific location on the earth. Is it going to be the same everywhere? No. There's the spoiler alert. No, it's not. And so that's why all of us all over the globe are going to be doing this simultaneously. And then what we're going to have, and I'm going to have the dates for this announced soon, we're going to have the Equinox after party. There's actually going to be 2 of them, 2 Equinox after parties, where you and a bunch of other people all over the globe, we're going to all kind of tune in at the same time, right? And we'll get on a Zoom call and people will compare. Like, okay, I was in the southern hemisphere and I saw this. I was on the Tropic of Cancer and I saw this. I live on the equator and I saw this. I live up in Point Barrow, Alaska, and I saw this. So everybody's going to get their little bit of a different thing. Right? Now, it's going to be really, really, really cool. So I want to show you how to track the path of the sun in the sky. And we're going to use 2 systems for this. And because, and when you're doing this, there's 2 kind of essential things that you're going to be kind of paying attention to. One is, what direction is the sun? So imagine at sunrise, right? Exactly what direction is that? Now, obviously, the tool that really helps you be able to do that is a compass. Bing. So having a compass is going to be really good. In a moment, I'll show you a specific recommendation for a compass to get. If you already have a really good compass, that is one of these ones that has a sighting mirror on it. And it has an inclinometer. And the inclinometer is, if you see this little red arrow right there, as I tilt my compass, that always points down. Ooh. Right, we'll be using that. You may have a chance to use some of that. So if you've got one that has this, like a Silver Ranger, you're good to go. If you don't have that, you can go buy yourself a Silver Ranger, but they cost a lot of money. And this is the little $11 cheap knockoff of that, and it does most of the same thing. So you can get yourself a really good compass. And we're going to be learning a lot about how to use that. So by the time you're done messing with this solstice, I'm sorry, equinox, I've learned all sorts of other things. You've learned how to like shoot bearings on a compass. You're going to be, you'll understand the difference between true north and geomagnetic north. Ooh. So this is going to be, there's going to be a big learning curve on this day, and it's going to be cool, right? So there's two things you want to know. One is, what direction is that sun, right? The other is, how high is it in the sky? Now, right when it comes up, it's easy to tell how high it is in the sky. It is at 0 degrees. It just like pops up like, ah, there's the sun at 0 degrees, right? It is 0 degrees above that, like 90 degrees is straight up over your head, right? And that's at 0. But then it's going to start climbing in the sky. So you're going to want to keep track of how high does it go and what direction is it, because those are both going to be changing as it goes through the day. It's going to be changing its direction generally from east to west, right? And it's going to be changing its elevation. How do you keep track of those two things? Now, and then how do you record this? If you record this as a big data table in your journal, it's not going to make sense to you. So also what we're going to be doing is recording our data in a way that visually makes sense to us, right? Because we're training ourselves to be visual thinkers and document data in a way that makes sense in a picture. Because the way our brains think in pictures it's much more useful than sort of seeing something in a data table, right? Now, let's take a look at some resources to help you do this. I am going to jump over to my website, which I've just redesigned, and I'm very pleased with. Look at that new little banner up there, attention, curiosity, wonder. I just think that's cool. So if you haven't signed up for the Wild Wonder Conference, oh, you can. And so more, so I've got all these different kind of cool little links that you can go to. Just wanted to brag about that because I spent a lot of nights up messing around with that. But I'm going to go over here to Nature Journal Land and pull that down to the Solstice and Equinox Journal. And when I click on that, this page pops up. Well, let's take a look at this page. What is on here? These are things to do on the solstice and equinox. Now, number one is make nature observations. Yep. We're going to do that. Now, number two is how to make a sky diagram. And oh, this reminds me, I've got to run across the room here. Sorry, I meant to have this journal in my hands when the class started. But we're going to make a sky diagram, and I'll be, what that is a landscape drawing of your, of a place nearby where you have a good view of the sky that is 360 degrees. So mine goes from north to north, and then I'm mapping the path of the sun across the sky, where it is from east to west, and how high it is in the sky. And I'll give you a little bit more information about that. So for making a sky diagram, I have all the instructions about how to do that right here, right? And if I, there are also some hyperlinks in here if you need to learn more about how to use your compass. So this is going, will key you into, you get yourself a little compass. There's some links here that you can use to help you use your compass more accurately. So that is task number one. Let's take a look at my journal, and let's stop share for just a moment. Oh, hold on. There's people in the waiting room. I got to let those people in. I thought that I had deactivated that waiting room. Let's see here. Admit all. Hey, folks who are over there in the waiting room, sorry for having you wait over there in the waiting room. I thought that I had deactivated my waiting room so you wouldn't get locked out there. Welcome back, Melinda. And I'm going to try to find Melinda in my little chart here and make her my co-host because she always helps me a ton behind the scenes. There you are. I'm going to make you a co-host. Melinda, welcome. Sorry for starting without you. Now, I'm going to go to my little video. Oh, go to my video camera. And I'm going to show you what my, what did I call it? The sky diagram looks like, and then how to set yours up. Then we're going to go and show you another really cool activity that we can do. So here's the sky diagram. Let's grab this. I have a journal right here. Here it is. Right, what I have is along the bottom, I have directions. So if I live in the northern hemisphere, south is in the middle. If I live in the southern hemisphere, you're going to put north right in the middle. The details on that are on that web page that I just showed you. On the sides, you're going to go from north over here to north over here. So north to north. So if you were to take your journal page and tape it together like that, it would be, you'd be sitting in the middle and looking all around down in there. So north to north on the side if you're in the northern hemisphere. And then you can break it out a little bit more specifically. So you're going to have east, south, west, and you can put the degrees in. So I recommend just taking a, some little measurement tool. You could use something like this. And what you can do is across the bottom of your page, all right, let's say here's the middle of my page. I'm just going to use the centimeters that are marked on here. So if this is 180, I'm going to say this is 160, 140, 120. So I'm going in $60, 40, 20, 0. So right here on my map is going to be north. East is going to be right between at 90 degrees. Here's east. And this is going to be north at 180 degrees.
It should be south.
And then I'm going to do the same all the way out here through west to north again.
Jack, you want to make the middle one south.
Oh, sorry. Thank you. I'm thinking southern hemisphere. So yeah, here is south. So northern hemisphere, it's going to go north, east, south, west. Southern hemisphere, it's going to be south on the side and north right in the middle. All right. And so then I'm going to have west back to north. That's how you set up the bottom of your journal. And then what you're going to do is you're also going to have some landmarks going up into the sky. And I'm going to use a different scale going up. So 10 degrees on this horizontal scale that I have here is about that far. But I'm going to actually use a longer scale here. I'm going to actually have this be 10 degrees going up. So I'm going to have an exaggerated vertical scale, a greatly exaggerated vertical scale. So this is going to be 10, 20, 30, 40, 50 degrees, 60 degrees, 70 degrees. If I use a narrower ruler, I can get more into that. So if I'm just imagining like this is my sketchbook. You notice here on this sketchbook, when I lay it out, right? And when I do it this way on my journal and have a spread page, south is right in the middle of my book. And I am able to go all the way up to 90 up to the top of my page, right? Because I'm holding this little demo piece a little bit more sideways and trying to represent that all on one page this way. I wasn't able to get that far, but you get the idea. So I'm going to write in, here's 10, here's 20, 30 degrees, 40 degrees, 50, 60, 70. You're going to go to 80, go to 90. So that's my grid. That is my grid. And if I get that on a piece of paper, I am ready for recording this. However, I can have a little bit more fun if I want to, because I can go along this, I can get out my compass and find out what object is due south from me. Let's say there's a really tall building there, and I can see that against the skyline, right? And then over here in east, that's where the telephone pole sticks up. And so I can get a few landmarks in over here, and you just use your compass to shoot a bearing on that landmark and find out what direction it is from you. And you put in a few of those, like the tree is over here. And then you can draw the drawing to fill in all the things between those. There's another building over here. There's a few kind of landmarks in there. You can get this kind of a drawing of the horizon. Then you see the mountain that's over there and a little tree. You can get a little 360-degree drawing. Again, when I did that over here, mine looked like this. Now, because of the exaggerated vertical scale on this, I did the exaggerated vertical scale on this as well. So on my little drawing here, this was a round tree. It was a round lollipop-shaped tree. But because my vertical scale is exaggerated, it ends up being this long, tall tree. So that's kind of a, be aware that if you're exaggerating your vertical scale, that will be kind of a brain twister. Right? But I draw this in.
Well, we have a question while you're talking about doing the horizon. I'm not sure if you're going to address it. Someone was asking, how do you get the right height for the landmarks?
Well, whoever that was, thank them for a beautiful segue.
That's Barbara.
Right? Because we figure out where things go by using our compass, right? And you just have to put in a few key landmarks, and then by eyeballing it in, you can put in everything else. But you put in a few key landmarks, and then you can kind of fit things in. But exactly, if you've got this exaggerated vertical scale for the sky, how high do you make things go? For instance, this is a tall tree. It was closer to me. Do I put it up to here or down to here? Well, I'm glad you asked, because let's turn, the key question here is whether you're talking about the height of a tree or the height of the sun in the sky. How do you figure out how high to make these things? right? We figured out where they go here. Now, how high do you make it? And again, this could be for drawing in this tree, or it could be for putting in the sun at different times. And whoever asked that question is my new best friend, because they will make for this beautifully smooth transition. So let's take a look at how you might want to figure out the height of an object in the sky. Glad you asked. This is, we're going to jump back for a moment to this web page. Here's activity number 2, the sky diagram, and it's telling you to do the same thing which we talked about here. It tells you what to do in the northern hemisphere, tells you what to do in the southern hemisphere. Ignore this little section for now. We'll come back to that. Oh, who's that happy guy? And then there's a section down at the bottom is how to estimate or calculate the sun's altitude in degrees, right? That's how high is the tree, or how high is the sun. And there are several really cool techniques which we can do in order to do this. And some of them work really well when the sun is close to the horizon. Others work really well when the sun is closer to your zenith, more straight up. So depending on the sun's position, I will use these different techniques. Some of them are really just fun and raw mechanical. You get to use your body to measure the sun's location in the sky. Others are going to use beautiful trigonometry to calculate the answer based on measurements that you'll take. And I'm going to recommend that you play with both. It's been a long time since you did trigonometry, am I right? Right? If you did it at all, right? In my schooling, we skipped over trig, right? Somehow I missed the whole trig bus. And so my whole life I've been hearing people talk about like cosines and things, and I just kind of go like, ooh, that's one of them math things, right? And but it turns out that we can actually revisit it in our adulthood, and it's pretty cool. And so one of these techniques, it's going to involve trigonometry. And it's going to be really, really cool. Do not be psyched out by it. Don't be afraid of it. Dive into this and you'll be like, oh, wow, I see why people like this trig stuff. And you're also going to have a chance to then have this math, and it's going to apply to the world around you. A lot of people are math phobic because we were taught math as doing a bunch of calculations. That's just like if you were taught literature by everybody just doing rules of grammar and how to spell things, you would hate literature and books, right? So teaching math just as calculation would be the same thing. Math is a language that for describing the world, and it is beautiful as the world that it describes. And so here are some techniques that we're going to use. And I'll be kind of going through several of these. In a moment, I'll be demonstrating the 1 potato, 2 potato method, right? And this is a fun one because you're just going to use your body in order to measure the height of the sun in the sky. And this is the easiest, it's most intuitive, and it works great, especially when the sun is lower in the sky. The second is this cool way using tangents, so trigonometry. And with this, if you measure if you measure the height of, if you have a post with a known height and you can measure its shadow, you'll be able to calculate the sun's angle in the sky. And the directions on how to do that are here, and it involves a tangent table. We'll be demonstrating that in just a moment. Another way is if you don't want to do trigonometry, but you have a post, this could be just a pencil stuck into a wad of clay on your patio, and you measure in centimeters how high that pencil is and measure how long its shadow is. If you don't want to touch trigonometry, you can figure out the sun's angle in the sky by, let's say that post, your pencil is, it's 23 centimeters long, right?
and its shadow is 37 centimeters long. This just calculated right down here. Here's the sun's angle in the sky. For a post this high, a shadow this length, here's the angle. And you can do this with any measurement. If you're using inches, just put it just make sure you're doing your post height and your shadow length in inches or in millimeters or in centimeters, whatever it is, you put that measurement into both of those things, there's your sun angle, right? But we're gonna actually be able to do this same thing on our own with using a tangent table. I really wanna recommend that people try this because it stretches our brain. And the work that our brain will be doing in order to kind of work out how to do this with the tangent table is really, really great for our neuroplasticity and our opportunities to kind of challenge our head. You wrap your head around that little bit of math and you've got a useful tool you can use anywhere. You don't have to be, plugging it into this calculator. So now another one is the post and rope. This is a little bit more useful if you are teaching a class and you've got a bunch of students out on a playground. This year with COVID, probably nobody's going to be doing that. But in this, you would make a rope, tie it to your tetherball post in the middle of your playground. And this would allow, this little calculator here allows you to figure out, let's say I have a post that is 7 feet tall, and I want to know how far out along that rope I would go in order to make a little mark that would represent where 20 degrees is. I would put 20 degrees in here. I would go out 19.2 feet on that rope and I would make a little mark. And if I was doing it to get 40 degrees into the sky, that would be only 8.3 feet out. So what you would be doing here with this technique, again, most of us are probably not going to be doing this because you're not going to be doing this with a large class. If you are doing it with a large class, kind of read this over because this would be kind of a cool, fun thing to do. It'll be kind of doing things in a little bit of reverse. This next one right down here, I have a little video on how to do it, but this is really neat. And this, if you have a compass that has a clinometer on it, so that is that little, the clinometer is, I'm going to jump back to the jack cam here. Hi. So again, the clinometer is that little red arrow dangling on the bottom of my compass that you can see rocking back and forth. The way this works, if you have a compass with this, is this compass dial here spins, and I spin it so that it is lined up east-west this direction here, east to west. And that puts this, notice that puts this little kind of degree reading thing on the bottom of your compass. And then what you do is you can actually use this for all sorts of things. So if you're a geologist and you're trying to figure out the slope, the dip of a slope of rock, so the angle that a slope of rock is going down, you just take your compass and put it along that rock face. So it's now resting on the rock face. And look, you can read off in degrees the angle of that slope. So, or if you are studying avalanches and you're going like, at the angle, there's a big difference between like, are you a 60-degree slope or a 50-degree slope, right? So you'd be out there with this and kind of holding it up and averaging kind of the slope angle, and you then read it right off the bottom here. How many degrees is that angle? So you can use that same clinometer to measure the angle of the sun in the sky. And here's the way you do it. Do you see this hole in the front of my compass? That is my sighting hole. and I aim at objects, and I can figure out an angle from my eye to that object. So if I aimed this up at the sun, I could then look in the mirror, and in the reflection of the mirror, be able to read the angle to the sun. The only problem with that is when I would be aiming up at the sun through that hole, I go blind because I'm now staring at the sun. Safety point, don't stare at the sun. So what I do is I'm going to actually, instead of looking at the sun, I'm going to take this and I'm going to stand with my back to the sun. So the sun is behind me. And I'm going to look down on the ground in front of me, and I'm going to find some little object like a pebble. And I'm going to move my shadow around until that pebble is right in the middle of my head. So right at this point, right between my eyes, in where my shadow would be. And so for people who haven't done human proportions, that's exactly the halfway point through the head. If you can see your ears in your shadow, if you have short hair, it'll be at the height of the top of your ears, right? And then in the middle of your head. So you take a little pebble on the ground and you put that little pebble right in the middle of your shadow, of your head. And then what I do is oops, I'm holding this upside down. I line this corner of the string and this little tab up so that I'm looking straight down through my target hole. So I first line my string with that nub and I sight through the target hole. There's actually a little aiming mark on it. And I point that at the pebble. And then in the mirror right here, I can turn that to be able to read. Right now I'm holding this at 40 degrees. So you can read the degree down to the pebble off your compass. And if you're to draw a line from that pebble through the middle of your head up to the sun, that's exactly the same as the angle. So the angle from the pebble to your head is the same as the angle from the pebble to the sun, the angle of the sun. So that's a really cool way of doing it that involves a compass with a clinometer and a pebble. That's pretty neat. Let's also take a look at this 1 potato, 2 potato method. And what that is that if I stand with my back to the sun, so my shoulders are square, the shadow is pointing in front of me, or if I'm facing the sun, I want to be at right angles to it. So I'm looking towards the sun. And I want to figure out the height of the sun. Now I have to do this without trying to get myself to stare directly at the sun, right? And what I do is I take my fist and I hold it straight out in front of me and bring it into my center line. And I'm going to hold that right up so that my fist starts at eye level. So the bottom of my fist will be right at my eye level. Arms straight, shoulders square. The height of my fist at full extension is about 10 degrees. And everybody, yeah, they've got different size fists, but they also have different size arms. And we take all those things into account. For all of us, it works to be about 10 degrees. So what I do is I go, here's 10 degrees, here's 20 degrees, 30 degrees, 40 degrees. So I do 1 potato, 2 potato, 3 potato, 4 potatoes. 4 potatoes, that's 40 degrees up there. So if I get to 3.5 potatoes, that's 35 degrees whoop, up in the sky, right? So you can do the potato, right? A little dance move, right? And that gets you the height of the sun in the sky using the potato method. So again, shoulders square, I'm looking at my target. 1 potato, 2 potato, 3 potato, 4 potato. 4 potatoes, 40 degrees. That's pretty cool. So that's what I recommend. I recommend doing the potatoes for the height of the tree, right? So let's now take so that gives us a way of figuring out how high the sun is. let's take a look at one last thing, and that is this technique using trigonometry to get the height of the sun, because I think this is beautiful, beautiful math. If you go to that page that I have, you'll see where I've got a place that you can go to NASA's website and download this tangent table. And it's fun just because, number one, you're going to the NASA website, because so you're thinking like, wow, that's really cool. I'm going to the NASA website to download a reference piece. And it's about math. This is just like, bless you, NASA, for having like tangent tables online. Now, here's the way that this is going to work. If there is a post of a known height, and the way you figure out the known height of the post is by measuring the post. So this can be any vertical post. This can be a fence post. This can be a pencil in a lump of clay. This can be a volleyball post in the middle of your school playground. You measure the height of the post. You can use feet. You can use centimeters. Whatever you do, just make sure that you use the same units of measure for the vertical and the shadow length. So you're going to measure the post and the height of that post's shadow on a 90-degree post. If you get those two pieces of information, you can calculate the height of the sun in the sky. So by the way, if you are using inches, don't convert those to feet. So don't say 5 feet 8 inches, just give the total number of inches, right? So just ignore when you get to 1 foot, 2 foot, right? So, so here we go. What you're going to do is A here, A is the height of the post. And what I do is I do A divided by B. And B is the length of the shadow. You do that calculation, A divided by B. Now, let's say I do that calculation. You can do that either in your head, a piece of paper, or use a calculator, right? You calculate that height of the post over the length of the shadow, and you're going to get a number. So let's say my number was 0.57. I would look at this table here, and I would say like, okay, 0.0, 0.2, 0.4, 0.5, 0.5, 0.57. 0.57 right here. That means that according to this table, that sun is 30 degrees up in the sky. So that angle right there pointing to the sun is 30 degrees. So if I do height of the post over the shadow length, put it into my tangent table, that number I get turns into my angle when I put it into my little tangent table. Isn't that beautiful? It's really, really neat. So this is, I recommend everybody try this. Even if you're like, oh man, I didn't take trig either, or I've forgotten everything that I learned in my trig class. That's okay. Bust it out, dust it off, play with it, and it is an invitation for your brain to kind of wrap around some really cool, useful stuff. Now, let's take a look at the other really cool thing that I've got going right here. Sharing this page again. So we looked at this. We talked a lot about getting the height of the object, but look at this right here. Activity number 3, the sun target. What you're going to do to get started is, all the directions are here on how to do this, but you're going to get you started, you're going to need to print out one of these sun targets. I want to send out a shout out to Shirley and David Adams, who helped me develop, who actually did all the hard work in developing this cool system of playing with the sun's shadow. And see, what you're going to do, you're going to pick one of these. If you are in sort of mid-latitudes in northern hemisphere, choose this first one.
The next one here works for low latitudes in the southern and northern and southern hemisphere. At low latitudes, shadows are shorter. The closer you get to the poles, shadows get longer. So that's why we need some different targets for those different ones. We've got some that work well in the southern hemisphere. We have others that work well in the northern hemisphere or mid latitudes. I'm going to choose this one right here. So if I click on that, it brings me to this page, and that's a page that I can download this, right? So I can go right there, click print, and it's going to print this out onto a piece of paper. So I'm going to go print right now, and then walk across my room to my printer, pull this out, and look at what I have. All right. Here it is. There is my sun shadow target. This is going to be really useful, really fun. When I was doing this the first time, I discovered that the patterns that I was looking at a big volleyball pole in the middle of a playground. And what I started doing is just drawing the length of the shadow at different times of that volleyball pole. And it made this really neat pattern. The shadow lengths changed, the directions that those shadows were changing. And I realized that pattern was really elegant and really, really interesting. The only problem with this was that when I left the playground, all that data remained on the asphalt of the playground. And when people played volleyball the next time, they stepped on it and it got erased. So this is going to allow you to have your own volleyball pole. And when the event is over, you get to take it with you. And here's the way it works. You print out your target, and you'll notice that on the bottom of the target, I'm going to zoom in on this. This is just brilliant. Look at this. Here's a little thing. You see these two little arrows here? This says length of the shadow post. That means for a target that is this size, this is the length of the shadow post you need. So that means if I had done a reduction of this whole page, this line would also be reduced and it would still work. If I did an enlargement of this and made it really big, I would get a longer post. Let's say I was doing a demonstration for a group of kids, and it would still work. This is relative to the size of the circles here. What I'm going to do is I'm going to take a little toothpick, and I'm going to put one end here, and I'm going to mark on here the length of that shadow post. And then I'm going to take a pair of kitchen shears, snip that off, and double check that I have trimmed that to the right length, and I have. Right? I now have a post that is the same size as that little line there. Welcome to the middle of your target. I now am going to take a drip of glue and put a little drip of glue, just a little dab will do ya, right in the middle of the page. And while that's still wet, I'm going to put my little post in it and move it to the very center of the target. And I'm going to look around from all sides because I want to make sure that this is vertical, vertical, vertical. I want this to be straight up. So as I spin it, looking at it from the sides, yep, that's straight up. Now, once this dries, I am good to go. All right, I've made my little, here's my volleyball post. And what I could do is just put this out on the ground and at different times measure the length of the shadow by just tracing in over the shadow. That would be pretty cool, but I can make it even cooler by first orienting this whole piece of paper to north. If you've used a map and compass before, you're familiar with the idea that there's north on a map, and you use your compass to get north
on the map, if that direction there is north, I want to turn my piece of paper so that that is pointing towards, so if I say like, this is north on my map, my finger's actually pointing north. That's called, when the map is oriented, that's the way it works. So if I were to say that's north on my map, if my hand is actually pointing towards north at that moment, my map is oriented. I want to orient my sun target. And the way I do that is kind of interesting. I'm going to swing this out, go here. All right, here's our globe, right? This spot right here, where the whole thing, there we go. The spot on the top where the Earth spins around, that's the North Pole, right? So the whole thing pivots around that point. The problem is your compass doesn't point to the North Pole. The thing that makes your compass work is that there is a mass of molten iron in the center of the Earth, and it's churning around, and from its movement, it sets up an electromagnetic field that then is projected out through the Earth. And actually, that electromagnetic field is amazing. It protects our planet from all sorts of harmful rays from the sun. If that little electromagnetic generator in the center of the Earth turned off, we would be destroyed. Life would be blasted by these really damaging rays from the sun. So that's a problem when you're, let's say, doing a Mars mission. You need to develop, how are you going to shield your astronaut from these dangerous rays from the sun? It's a really big problem. Same thing on the moon. If you're going to have people on the moon for a long period of time, same problem. So this electromagnetic field of the Earth has a North Pole and a South Pole, but they're not at the North Pole and the South Pole of the Earth. So north, the place that your compass points to is about in, let's see, here we go. It's about here on the globe. So it's near the North Pole, so it's north-ish. And it's also interesting, it actually changes location over time. It's traveling, right? And so every once in a while you have to, and then this projects this field of electromagnetism around the Earth. It doesn't go in perfectly straight lines, but thanks to science, people have mapped the shape of that. And so you can figure out for any place on the Earth, there's an error factor called the declination. And if you take that error factor into account, you can get your compass to point to true north. Right, so here's how we do that. I'm going to figure out my error factor, and the way that I do that is by going online to a website. If you go to that same page that we brought up earlier, there will be a link to a website to help you plug in your address. It will give you your declination. So for where I am on the Earth, it is about 13 degrees east. Hold on a second. I need to rotate this. Oop. Oh, no. One more time, boop. There we go. All right, so from where I am on the Earth, it's about 13 degrees east, which means that from true north, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's going to be that far off when my compass needle is pointing there. That's the difference between where my compass points and where true north is. When my compass needle says that's north, really north is over here. So what I'm going to do is I'm going to draw a line from this little plus mark back here all the way up along there I go. And I draw in a little line here. All right. Now, what I do to
to get my compass oriented, is if you look down at my compass, let's zoom in on it, you're going to see several different things going on here. There is this red arrow, that's your north arrow. There's also a box, a red box, an open red box. And I've taken this and I've turned this so that north, it lines up with that red box. And I'm going to spin that so that north, see the little N there, goes right under this dot here. And then what I do is if I spin my compass to get that red arrow inside that box, so the people will say to put red in the shed. So there's put red in the shed. All right. That, this is now, this is pointing this way to magnetic north. So check this out. If I put my compass alongside, see that little purple line that I drew? I'm gonna just line the side of my compass up with that. All right. Now, I spin the map and the compass together until I put red in the shed. Boom. My compass is now oriented to true north because I lined it up, right? I'm lining, this compass is aligned with magnetic north. Oh, look at the magnetic pole of my pencil. That's cool. So this arrow in here is aligned to magnetic north. This is lined up to magnetic north. And that means that this whole piece of paper is lined up both to magnetic and true north. So it is oriented. I would then move this and I'm ready to go. I'm about to bring you outside and show you what you can do with this. In order to do this, I'm going to switch the spotlight over to, I'm going to unmute myself, cancel the spotlight. And hello, hello. All right, that's the one I want. I'm going to spotlight this. So just come with me, and we're going to go on a little walk, and we're going to go outside here, and I'm not going to put my I left my compass inside. Now we're going to go back faster. Oh, there it is. Say hello to the whiteboard with all my thoughts and thinking. And here we go. All right, so I'm not going to put it down here on this table. I don't want to get it anywhere near metal objects. That will just really mess with your reading. I also want to make sure anywhere I'm putting it down on the ground, there aren't pipes or electric wires running under there because they have their own electromagnetic field. It'll mess with your compass. So check this out. I know that there aren't any of those things running underneath this part of the patio. So I'm going to put my piece of paper down here. I'm going to turn my camera down. Melinda, please unmute yourself, and you're going to have to guide me.
Yeah. Sure.
Melinda, are you looking at, can you see the my little target?
Yes. Although the harsh shadow.
I can't hear anybody. Yeah. All right, Melinda, when I hold it like this, can you see my target?
I can, but the issue is the shadow is really, if you put it in the shade, it's easier to see. There we go.
Okay, so let's first orient this bad boy. Can you see this part right here?
Yes.
All right,
So I have this thing lined up, as I said before. I am lining the side of my compass up with that purple line that I drew. And I'm going to spin the whole thing to put red in the shed. And woo, we still watching it?
Yes, we can see.
All righty. Bam. All right, this piece of paper is now oriented. So what I might do if I would have this out all day is I'd get some tape and I would just tape this down in this location. I can then leave it here. All right. And if I move myself out of the way, look at that. Can you see the shadow of, Can you see the shadow of the post?
Yeah, we can see the shadow.
All right. So what, well, I'm going to grab this. Melinda, what time is it?
It is 1:07.
All right, 1:07. Just double check that I feel that blowing around in the wind. So what I'm going to do is I'm going to just trace the shadow right now. Up to here, I'm going to write 1:07 p.m. Now I just leave this out here all day, taped down. And at different intervals, I'm going to come and I'm going to draw in different shadows. I'll just trace in different shadows. And that is going to end up with a really interesting pattern because those shadow lengths are going to be changing throughout the day, right? Those shadow lengths will be changing. And the directions of those shadows will be changing. Now I have to mute this thing so I don't get feedback.
All right. So let's just come on back here for a second. Oh no, I don't want that. I want this spotlight here. Aha. So look at that. I've got my first little reading right there. And I'm going to get a whole bunch of different lengths and different times. Now, let me show you one reason why that you could, if you just have a blank piece of paper, a piece of white paper, and you glue a vertical stick on it, you can put little marks in it throughout the day, and that's cool. But the reason why this sun target is so cool is look at this. I want to show you two other things like this, and then we're going to call it a wrap for the day. Look at this. This is just so, so neat. The first is, for a shadow of this length, what angle is it in the sky? Well, I'm glad you asked. And that's what these circles are for. Notice that this line comes to a little bit less than halfway between 50 and 60 here, closer to 60. So this is about 56 degrees. Right? If it was right on the 50 line, it would be 50 degrees. Here it'd be 60 degrees. Here it's about 56 degrees. So how high is the sun in the sky right now? It's about 56 degrees. Isn't that neat? So the circles tell you the degrees in the sky. But wait, my friends, there's more, because if you were to project that line out, right? See how I'm lining up along that shadow line all the way out to here. Where does it cross here? Oh, look, it is, here's 180, here's 190. So this is probably 181 to 183. This is maybe 183 degrees. So this tells you the direction
This tells you the altitude in the sky, and you get the pattern of all the shadows preserved for you. Kaboom! Mind blown, right? Isn't that slick? I just love this little target. So you don't have to do all these things, but the more you mess around with it, the more fun it's going to be. And if you like go just full on down this rabbit hole on the equinox, you're going to be like it's going to be really, really neat. And it will open up puzzles and questions to you. What I want you then to start doing is start to ask questions like, why this, like this? What would it be like if I were here? Start trying to figure those things out in your head. Wonder like, if I compare this with somebody on the equator, do I think my lines are going to be longer, shorter? Kind of make some predictions. What do you think is going to be going on, right? And then on our equinox party, we're going to have a chance to hear from people all over the globe. At least from all the people who had clear skies. Hopefully yours will not be too smoky. If you kind of feel overwhelmed by this, and you're thinking like, just go out that day and bliss out and just make some observations of what's happening in nature. But if you are following these things also and making these diagrams, it's going to open up some doors to your thinking about this phenomenon that you otherwise wouldn't get. And I got to tell you, it will be cool. It'll be really cool. And so we're looking forward to the equinox. All those resources you can find on that link on my website. And you will also find a link there to, if you want to get one of these kind of low-cost compasses with a mirror and clinometer, you can find them. I've got a link to them there. I'm not selling these in my store, but you can get them online for about $11. And it's going to be fun. It's going to be a lot of fun. If you made records during the solstice, you might want to put your equinox measurements on the same page. Just use a different color and have those all going on the same page. And then you will see those two lines. You can compare them, right? And then we can also put our winter solstice on that same page. Right? You're gonna love it. It's gonna be good. It's gonna be good. You're gonna be there, right? Now, and oh, here's one last thing. I found that when I was making my measurements, eventually like a shadow came into where I was doing my stuff. It turns out that you can just pick up and move over to where you see the sun, reorient your little sun map, put it back down, and just keep on going. So if a tree shadow gets where you want to be, you can handle that. It'll be okay. Just don't walk 500 miles. Right, just go over there, and as far as your little target is concerned, it'll be good. So I can't wait to share this event with you all over the world. We're going to be looking at these things. We'll be sharing our observations. We're going to be thinking like ecologists, thinking like naturalists. It's going to be a lot of work. I do want to recognize again the help and the contribution of Shirley and David Adams, who developed that whole sun target system. It's so elegant. Behind that is a lot of really beautiful mathematics. Really beautiful mathematics. And I really appreciate and respect them for their work in developing that.